Okay, yes, I will be giving 3 lectures on arithmetic groups, and all 3 lectures are essentially independent of each other. So just if there's something you don't understand in one lecture, that's okay. The next lecture can be something quite different. But before I get started on that, I do want to thank Professor Choi for inviting me here. I've never been to Korea, and it certainly is a pleasure to be here. Let's go ahead and see if we can start. Yeah, okay, yeah, so there's several topics I'd like to talk about today, but I think this is too much for an hour and a half, so we're not going to cover all these things. The main thing, though, that we'll talk about is, I want to talk about group theoretic superrigidity. I just want to explain what superrigidity is. It's a major topic in the theory of arithmetic groups. I'm not going to get technical, I just want to give an overview, an idea of what superrigidity is, and give some examples of superrigid subgroups. But that's a group theoretic topic, and my audience is algebraic, so I want to give some sort of geometric motivation to it. So I'll start out with something that's quite different, something very elementary. I'll start just by talking about linkages, which it's a very, very elementary topic. And we'll see what superrigidity means for linkages, and then I'll explain what it means for groups, and then I'll explain that actually these are really, they look like 2 completely different things, but I'll explain why they're different versions of the same idea. So I'll talk about the analogy. The main thing though today, it's okay if you don't understand linkages or the analogy. The crucial thing is, today I want to talk about group theoretic superrigidity. That's what we're going to do. We'll talk about group theoretic superrigidity, do some examples, and then I think I'll have time to prove a very important theorem called the Margulies arithmeticity theorem. So this is really my goal, is to explain why superrigidity implies arithmeticity. And I don't think there'll be time to talk more about this last part. But if there is, we'll talk about some geometric consequences of superrigidity. But also, I should say, I've prepared all these slides, so I have an idea of what I want to talk about, but it doesn't really matter what I want to talk about. If there's questions or I end up doing something else, that's okay. And I should have asked, this is a chalkboard, right? So I can write on it if people have questions? Yeah. Okay. Yeah, so let's go ahead and start. And this is the outline of what I ideally would do, but in an hour and a half I won't be able to do all this, but anyhow, we'll get some idea of what superrigidity is. That's what I want to do. But before we do superrigidity of lattices, which is group theory, as I said, let's just do something very simple. Let's just take, for example, 2 triangles put together. So here's a picture of it. It's made out of 5 sticks, so we've labeled these sticks. I don't know in Korea, but in the U.S. we have, sometimes you buy something that's not put together. It says to take part A and put it in part B, and then part C attached to part D, and all this kind of stuff. Well, that's the idea here. In this example, we've got some sticks, A, B, A, C, and the rule is just glue A to A. Glue the end of one stick A to one stick B, and then glue the B to the B, and the C to C, and then you get something, and what you get is this object here, 2 triangles put together. But that's all there is to it. So we're just building something out of sticks by gluing them together according to certain rules. And the crucial thing is that this example here is not rigid because you can move it. It can be deformed. So, for example, if you build this object, you can just open up the 2 triangles, you can change the angle between them, and I've got a picture of that, right? Yeah, the angle between the triangles is not fixed, just determined by this the gluing process. So, in fact, what we've got here is just a hinge, which is obviously not something that's rigid, it's flexible. Okay, so, this is an example of a flexible linkage. We're going to give another example. A tetrahedron. So in fact, all I'm going to do is take that hinge and put 1 more stick in here. If I connect A to D, I have 1 more stick, so now I guess I've got 6 of them glued together. And this linkage, or this figure, is rigid. It has no deformations. It's solid. No matter what you do, it won't move. Okay, so that's an example of a rigid linkage. But now I want to make another example. This one, I'll take my tetrahedron that we had and put another small tetrahedron down on the bottom here. So I've added another tetrahedron at the bottom. I just put a point E and connect it to the other 3 points. And now I have 2 tetrahedra glued together. And this, again, if you think about it, I mean, I'm not going to prove this, but I hope it's clear, this is rigid. Right? The one tetrahedron is solid, the other tetrahedron is solid, they're stuck together solidly, there's no way to bend this. The points won't move. This is another example of rigid linkage. So this is very elementary and obvious, but what I want to explain now, the crucial thing here is that even though this linkage is rigid, it's not what I call super rigid. So let me explain what super rigid is. The reason this is not super rigid is that if this was a present you were going to give to a child and you had to assemble it together, and these were the rules, these rules are not enough to get the right toy. You can put this thing together properly So after you take it apart and have these sticks, if you put the sticks together, following the correct rules, you might get the wrong object, because that little triangle at the bottom could be inside instead of outside. I've assembled, I've got all the sticks glued the right way, but I got the wrong thing. I did not get, this is definitely not the same object, it's not congruent to what I wanted. So that's why this is not super rigid. It's rigid, once you put it together it won't move, but the problem is if you take it apart and put it back together, it might be put together incorrectly. So a super rigid structure, a super rigid link, is one that's guaranteed to get put together the right way, just if you follow the instructions. Okay, so I hope that's clear enough. Okay, so if we take two tetrahedra that's rigid but not super rigid, our earlier example of a rigid linkage was the tetrahedron, and this probably is clear. This is super rigid. If you just glue those sticks together, put A to A and B to B and C to C and so on, you'll definitely get that same tetrahedron we started out with. And what that means is just the combinatorial description, just saying to connect the sticks in that way, completely determines the geometry. So combinatorial data completely determines the geometric structure. That's what super rigidity is. So let me... Yeah. Good point, actually, yeah. So the point was that actually if you follow the combinatorial instructions, you might end up not with the original structure, but with the mirror image. So, yeah, that's a technical point. I'd say it depends how you look at it. Most people would say that's not the same, but if you allow reflections, it is. So, in fact, yeah, we'll get to that. That's a very good point that actually you might not get the right toy because you actually get two different toys in our universe, but if you allow things to be reflected, well, if you just take mine and look at it in a mirror, then you'll think out the right one. But yeah, that's a very good point. So, and if we're actually going to talk more about geometric combinatorial superrigidity, I'd have to address that more carefully. But yeah, let me not throw all that. Okay, absolutely right. You could get a mirror image, and I'll mention that again later when I talk about it more carefully. Okay, so combinatorial superrigidity. Let me give a more precise definition, and then we'll address that point about reflections, although I don't think the notes do. Combinatorial superrigidity means that if you make a copy of the object, whatever object you've got, and you just obey the combinatorial rules, so that means glue the right sticks to the right sticks, then the copy you get will be exactly the same shape as the original one. Okay, that's what combinatorial superrigidity is. And what I want to talk about today, though, this is elementary, but it is a research subject, but it's not anything I really know about. I'm just using it as an example or a motivation for the same idea, superrigidity in group theory. That's what I want to explain, is what superrigidity is in group theory, because I think it's very easy to see what it means in combinatorics, and if I just say the group theory definition, well, it doesn't make much sense at this time. Okay? But anyhow, so let's go ahead and talk about the same thing, but in the theory of groups. So I'm going to talk about what superrigidity means in group theory. And here, the setup, it sounds different. Instead of having a bunch of sticks, what I'm going to have is some group. And in fact, I need not just a group, but a group homomorphism. So suppose I've got a group homomorphism. Let me call it phi. And it goes from the integers into RD. So the real numbers, so this is to the additive vector space RD. Well, and let me just, I know this is too elementary, but I just want to make sure we're not going to have confusion later. Homomorphism in this setting, the integer z is the abelian group under addition, and the operation in RD is also addition, so it just means phi of the sum is the sum of the phi values. And I know I don't need to say that, it seems like I don't need to say this, but the trouble is later it gets some multiplicative groups, and so we have a different equation. I just want to emphasize that here we're adding things, but if our group is multiplicative, then I'll have to use multiplication instead of addition when I have a homomorphism. But the point is, all right, so suppose I have a group homomorphism, it's defined for all integers. Well, it's easy to see that then you actually can extend this homomorphism to another homomorphism. I'll call it phi hat. So I'm going to extend the homomorphism we started that only makes sense on integers and let it be defined in all real numbers. And this is easy. Let me just give the proof. I can just define phi hat of any real number x to be just x times the phi value at 1. And let me just go through the proof here. So in order to check this is right, and there's, again, this is very elementary, but there's a point we get at the end that I want to say. Well, first of all, it's easy to define a anybody can make a homomorphism from R to RD, but we need this one to be an extension. What that means is we want to make sure that the phi hat values are the same as the phi values. That's the first thing. That's what an extension means, is that we keep the same values at all the integer points. The next thing is that phi hat should be a homomorphism. And there's one last thing that probably wasn't obvious to you, and that's that we also have to check that phi hat is continuous, and that's because whenever I say homomorphism, I always mean a continuous homomorphism. So we're talking about the theory of Lie groups, and in the theory of Lie groups, you don't look at, or topological groups, you're not interested in homomorphisms that are continuous. Okay, but all these three things are obvious. If you just look at, maybe I shouldn't say it, but it's obvious. If you just put a number n in there, phi hat of n is going to be phi of n times phi of 1, which is phi of n. Yeah, so all these things are easy. But I wanted to emphasize that whenever you define a homomorphism, you need to check that it's continuous, or else I wouldn't call it homomorphism. Right, so this is an easy example. Homomorphism defined in the integers can be extended to be defined on the real numbers. This is not a superrigidity theorem, but it's an easy version of a superrigidity theorem. What I want to get to soon is talking about what superrigidity actually is. This is too easy. Superrigidity is a more complicated version of the same theorem. So let's just start here. So for example, I think I hit twice here. Yeah. So what we just said is that if you have a homomorphism defined in the integers, you can extend it to be defined in the real numbers. Well, it's only a little bit more difficult. Certainly, it's just an exercise to show that the same thing works, and I hope everybody can see the difference here. I'm just putting a K on my Z. Whoops, I'm just putting a K on my Z. So if you have a homomorphism defined on ZK, on K tuples, that will extend to be defined on all of RK. And the proof is pretty much the same as before. In fact, we can do it let me just do it explicitly. So what we do is look at the standard basis of RK. So E1 is 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0, and so on. If we take the standard base of RK, I'll use that in place of the number 1 that I used in the last group. We can just define phi hat of any K tuple to be just the sum of x1, it's x1 times phi of E1 plus x2 times phi of x2, and so on. And in fact, we have to go through and check that that phi hat extends phi, we have to check that this is a homomorphism, and we have to check that it's continuous. But actually, all those things are obvious because you've all seen this before. For undergraduates, we teach them that a linear transformation can be defined to do whatever you want to a basis. A linear transformation can do anything you want to a basis, and the way you define the linear transformation is just by this formula. And the point is just that a linear transformation, it respects addition and scalar multiplication. Well, the fact that it respects addition means that it is a homomorphism of additive groups. Right, so that's it. Instead of actually writing down the formula, I could just say you can define a linear transformation to do anything you want to a basis. That'll give us a linear transformation. A linear transformation will be a homomorphism. Also, everybody knows that linear transformations are continuous. And so the only thing to check then is that the phi hat extends phi. But again, it's an easy exercise since the standard basis, E1 through EK, generates ZK. If you have a homomorphism that agrees on the basis, on the generators, it agrees everywhere in the group. So this is just an easy exercise. The details are an exercise to prove that, in fact, this does extend. Okay, well, again, this is too easy. Right? This is just a simple exercise. The point is, I want to do something more interesting to get a superrigidity theorem. Superrigidity is what happens when you look at homomorphisms not just into an abelian group like this, but into a more interesting group. Mathematicians don't spend their lives just studying homomorphisms into abelian groups. There are many mathematicians who spend their whole career in group representation theory, which means they study homomorphisms into matrix groups. That's where the action is. So the point is, a superrigidity theorem will be a theorem just like this, except we want to replace this stupid group with an interesting matrix group. That's what superrigidity is. So let me just get a little bit of notation here then. So in order to talk about matrix groups, let's look at the basic matrix group is the general linear group, and let's just take complex entries, for example. The B by T matrices over C. But I want this to be a group under multiplication, so I need my matrices to be invertible. That means I want the determinant to not be 0. So take all the matrices, square matrices with non-zero determinant, that will be a group under multiplication. And what I'm interested in, and what group representation theorists study, is homomorphisms into GLBC. That's it. So that's what we're going to do. So let's go ahead and state this. So this isn't even a theorem. This is just an observation. We'll make it a theorem if we replace this with an interesting group. Okay, so let's do that. Let's look at homomorphisms from the integers, not into just an abelian group, but into a group of matrices. Well, we'd like to extend that homomorphism phi. We'd like to find a phi hat that's defined in all real numbers. That would be a superrigidity theorem. The trouble is, that's not true. Okay, well, sorry. So we've got an additive group to multiple group. The problem is that if you have a homomorphism defined in the integers, it might not extend to a homomorphism defined in all real numbers. And let me remind you, though, I mean, I'm not sure if this is exactly right, but remember, I'm only talking about continuous homomorphisms. There's certainly not a continuous homomorphism in some cases. So let me just explain why. Okay, so here's the problem. When you look at the non-abelian case, when you look at an interesting group here, you actually have to be careful what you do. So let's suppose that every homomorphism does extend. Let's suppose that all homomorphisms extend. Let's suppose we've got this phi hat that's defined on all real numbers, and it extends the values on integer numbers. So it has the right values on the integers, but it's defined for all real numbers. Well, the crucial thing to notice, well, there's two observations. First of all, if we look at phi hat of 0, well, 0 is the identity element of the integers, and any homomorphism always maps the identity element to the identity element. So 0 is the identity element in Z. We then will map that to the identity element of GLDR, which is the identity matrix. So phi hat of 0 is the identity matrix. And now I just want to do an obvious calculation. So if you take the determinant of phi hat of 0, that's the determinant of the identity matrix, and the identity matrix has determinant 1. Well, I don't even need that. I just need to notice that that's something positive. Right? So the determinant of phi hat of 0 is definitely positive. That's obvious. Okay? And now the other thing I need to notice is just that the real numbers are a connected set. So if you take a continuous function, remember I'm only allowing continuous homomorphisms, if you apply a continuous function to a connected set, the image is going to be continuous. So phi hat of r is continuous. And also, so phi hat of r is continuous, the determinant is a continuous function, so we take the determinant of phi hat of r, that's going to be continuous. Sorry, connected, sorry. Okay, so if you look at the set of all determinants of phi hats of things, that's a connected set, and, well, it contains the number 1. It's a connected set containing 1. Well, it's some connected set in the real numbers, but the determinant of a matrix in GL is never 0. So it's actually a connected set in the real line with 0 removed, and it contains the number 1. Yeah, let me say, so my r cross just means r take away 0. So here's the real line. You take away 0. If you just look, well, we've got a connected set containing 1 someplace, I mean, in 0. I mean, I hope everybody sees what that means is that actually the entire connected set has to be to the right of 0. Everything's positive. Right? If you've got a positive number in the connected set and 0's not in it, you can't have any negative numbers. So everything's positive here. So that's the key thing here, is that if you have any homomorphism defined in the whole real line, the determinants are all positive. But that's, I mean, so in particular, if you take the determinant of phi hat of 1, well, phi hat of 1 is the same as phi of 1, so the determinant of phi of 1 is going to have to be positive. Okay, so from there, this is obvious if you put a hat on it, but a hat or not a hat gives you the same thing with 1. So the determinant of phi hat of 1 has to be, the determinant of phi of 1 is positive. But this was talking about any homomorphism. We said that suppose you take any homomorphism, then what we've proved is phi hat of 1 has to have positive determinant. But there's no reason to think that's true. I mean, the determinant could be anything. It could be, in fact, phi hat of 1 can be any matrix. You can define a homomorphism that takes the integers to GL, to a group of matrices, with phi of 1 being any matrix you want. In particular, it could be a matrix of negative determinant. So that's a contradiction. We proved that the determinant's always positive, but there's certain examples where it's negative. Right, so that's why not all homomorphisms extend. Right, and it's not it's not a major thing, but there is a problem. Not all homomorphisms will extend. Okay, so let me just say that again. What I just proved is that if you have a homomorphism defined on Z, it might not extend to be defined on all of R. And the problem was that you might have a matrix with negative determinant. And if you homomorphism, you start with a matrix of negative determinant, you can't put that into a connected set. Right, so, well, actually, yeah, phi of 1 might have negative determinant, but if you look at phi of 2, well, let's just calculate that. Determinant of phi of 2 is 1 plus 1. Right, so, and then I'll do a couple of steps at once. Phi of 1 plus 1, remember, we've got a homomorphism from Z, an additive group to a multiplicative group. So phi of 1 plus 1 is phi of 1 times phi of 1, so it's phi of 1 squared. But the determinant of a square is the square of the determinant. So what we get here is just the determinant of phi of 1 quantity squared. So, okay? And this If you square a number, square a real number, that's obviously going to be positive. So this problem doesn't happen. You don't have this trouble if you just look at phi of 2 instead of phi of 1. And in fact, if you think about it, the same proof shows that if you take the determinant of phi of any even number, that's going to be positive. Exactly the same calculation shows that. So what that means is, there's not a problem if we only look at even numbers instead of odd numbers, right? We won't have this problem. If you only look at even numbers, you're not having to have negative determinants, okay? So what that tells us is that if you're trying to extend a homomorphism, odd numbers might give you a problem, but even numbers look okay. So what we have to do is just ignore the odd numbers. So we restrict our attention only to even numbers. And so here's a picture that tries to illustrate what I mean by that. Suppose these are the values. Here's phi of 0, phi of 1, phi of 2, phi of 0, phi of 1, phi of 2, phi of 3, phi of 4, and so on. If we're trying to extend this to be defined on all of R, we want a function defined not just in integers, but we want to put a curve through all these points. And I try to make this an example so you can see that there's clearly not a nice curve that goes through all these points. But if you ignore the odd numbers, ignore the values that are down here. These are negative values. These are values that came from odd numbers. Then it's easy to put a curve through those. Put a very nice curve through those points. And that's exactly the situation I'm talking about here. Is that the odd numbers might give bad values, but if you ignore them, you can extend your function to be defined to hit all the values of even numbers. Okay, so that's just the simple fact that determinants might be negative. Right, well, that was very elementary. That was easy. That was obvious. The thing is that I hope you can believe that besides having to ignore odd numbers and restrict our attention to even numbers, there could be more complicated reasons that perhaps we'd have to restrict our attention not just to even numbers, but maybe for a different reason, we'd have to restrict our attention not to multiples of 2, but to say multiples of 3. It's not determinant that's going to do that, but I think you can imagine that there might be some other problems that come up. So we have to ignore everything except numbers that are divisible by 3, or maybe everything except multiples of 4, multiples of 5, or whatever. In general, I think you can imagine that if we're going to try to extend a homomorphism, we might have to restrict our attention to multiples of some number n. And that is indeed the case, that 2 isn't the only thing you worry about, but there'll be some number n that we have to restrict our attention to. And the thing is, this is talking like a number theorist, so talking about multiples of n. I want to say the same thing in group theoretic terms, because I want to talk about group theoretic superrigidity. I want to be able to talk about more general groups than just integers. So in group theoretic terms, the set of multiples of n is a subgroup of the cyclic group of integers. So what that means is, to a group theorist, we might have to restrict our attention, we don't say to multiples of n, but to some subgroup of z. And in fact, it's crucial to notice, I didn't say it here, I should have, this is not just any subgroup, it's a subgroup of finite index. There's only finite many cosets. We might have to restrict our attention to some finite index subgroup. So if you're extending a homomorphism, you can't expect to be able to extend everywhere. You can run into problems with determinants, or there could be other problems that come up. So you have to throw away some finite group, and then what's left you can hope to extend your homomorphism on. And it turns out that works in this case. And this, again, it's a little more complicated than what I did before, but it's a good exercise, maybe. It's a difficult but doable exercise. So if you have a homomorphism defined on the integer points of RK, so from ZK into GLDR, so it's from integer points in the group of matrices, then in fact, that phi will extend. Well, actually not. It might not quite extend. It might only extend in a finite index subgroup, and that's what this word almost means. I don't want to get technical, so I could say it virtually extends, because I'm restricting a finite index subgroup. But the word almost here just means that phi, my extension, phi hat, might not be defined on all of ZK, but just some finite index subgroup. That's all. Okay. It might not agree with phi on all ZK, but only a finite index subgroup. So phi almost extends means the extend, except that's if you restrict your attention to some finite index subgroup to a homomorphism defined little called phi hat from RK to GLDI. Right, so that's almost what a superrigidity theorem. That's the idea. We've got a homomorphism defined in a subgroup. It extends to be defined in the whole group, except there's this technical point. The reason I went through most of this explanation was to explain that you do have to pass defined index subgroup sometimes. Right, and that's what almost is. So don't worry so much about almost. Now that I've explained it. Think of it as saying that any homomorphism defined on integer points can be extended to be defined on all of RK. The trouble, though, is that this is not, in practice, this proposition just is not useful at all. We need one more condition. It's not enough to know just that phi extends. In order to get a superrigidity theorem, we need one more condition on phi hat. This phi hat should have the property that its image, if you look at the matrices that you get out of phi hat, those should be almost the same as the matrices you got to start with. They should be contained in this bar on the top is what's called the Zariski closure of phi of zk. So I'm not going to give a technical definition of Zariski closure. I think that'll come up in a later lecture. But if you know algebraic geometry, I mean, when I say Zariski closure, I mean what you know what is the Zariski closure. I do mean that. If you already know what this means. But instead of giving the definition, I'm just going to give some examples to get the idea here. But before I even give examples, let me explain why we need this condition. Without this condition, this proposition is just not interesting. And to explain that, I'll go and do an analogy. And I forgot, before I should say that the point of this proposition is this exactly, saying that homomorphism defined in ZK extend to homomorphism defined in RK with the image contained in the Zariski closure. That is exactly what it means to say that ZK is superrigid. That's what the definition of a superrigid subgroup in RK. A superrigid subgroup is one where any homomorphism defined on it can be extended to be defined in the whole group with control over the image. And let me explain, I'm going to explain why this condition is so important. And to do that, though, I'll first just give an analogy of something that's not got anything to do with what I'm doing here. But the idea of why I need this is the same as the classical theory of Lagrange interpolation. Lagrange interpolation says that if you have any set of n plus 1 points, you can always find a polynomial curve of degree n. So a function y equals, and then this is just a polynomial degree n, that goes through any n plus 1 points. So here's an example. Here's, I don't know, how many, 6 points. Okay. So that means there's a polynomial of degree 5 that will pass through all those points. And the trouble is, that polynomial, it'll hit exactly at these points. That's not the trouble, that's the good thing. So the polynomial will exactly hit through that point. The trouble is, there's no restriction at all on what happens between these points. And in fact, in practice, what happens is you've got these nice points. The polynomial between the points could go wild. It could do whatever it wants. And so here I try to give an example of that. These points, here's the points. There we go. So even though these values are fairly small, in between, the polynomial can get very large, positive, very likely. There's no control over what happens to the polynomial between the points. And that means, well, maybe it doesn't matter if you're a topologist, but if you're an analyst trying to do some kind of an estimate on the size of things, Lagrange interpolation is almost useless. Because even if you know that all these values are fairly small, the interpolated values, the values you get on R, are going to be something completely different. They've got nothing to do with what you start with. So Lagrange interpolation for many purposes is useless. And it's the same idea with superrigidity. So this Zariski closure is something like this isn't really right, but it's like the convex hull of the set of points. So in this example, if we had a bunch of points here, we'd like to know when we interpolate, when we connect up with a curve here, we'd like to know we never go above the highest point or below the lowest point. So if we put a bar there, we'd like all our values to stay in between. That's the convex hull of these points, of these values, of the y values. And we'd like a curve something like this, that stays inside that convex hull. That's what the Zariski closure does for you. The Zariski, saying that the image is in the Zariski closure exactly means that the interpolated values have to be controlled by the values you started with. Right? And so let me give some examples of that. That's the idea, but let me actually give some examples of that. So superrigidity says that a homomorphism extended, and this condition down here, the fact that the image is contained in the Zariski closure of the original image, exactly says that the image, the original image, completely controls the image of our new map. So if all the values of the original map are small, or in some sense, then in fact all the values, you won't interpolate the big values. So it's not size that matters. In general, good properties of the image that you started with will carry over to the interpolated map. You have control over the new map if you have control over the original map. So let me just give a couple of simple examples that come up all the time. For example, let's suppose that all the matrices in our original image, phi of zk, suppose all those matrices say they commute maybe. All of them commute with each other. Well then, it'd be nice to know that all the matrices in the new image, in the image of the new map, they should all commute with each other, and that's exactly what this Zariski closure will tell you. The fact that, if you've got a bunch of commuting matrices, then all the matrices in the Zariski closure will compute with each other. That's a basic fact of algebraic group theory. There's another example. If all your matrices, originally all your matrices fix some vector v, then all the matrices in the image of the new map will also fix that same vector v. That's the kind of thing that we have here. If you have some information about your original map, you'd like to also know that same information about the new map. If we didn't have this condition, then these properties would fail, and so this new extension would be useless. You wouldn't know anything at all about it except what it does to the integer values. So the point is, requiring the image be contained in the Zariski closure means that good properties, the original map, carry over to good properties of the interpolated map, the extension map. Okay, that's what superrigidity is. Okay, so the point is, this is an example of the superrigidity theorem, and it is a genuine theorem. It's not a particularly, I would call it a proposition, yes. It's certainly not difficult, but it is interesting. This actually is useful. You can use it for something. The trouble, though, is that we have some interesting groups in the range, but most group theorists aren't interested in studying just an abelian group. So the whole point is, what I want to talk about today is this same proposition, but generalizing it to look at non-abelian groups instead of abelian groups. That's when you get an interesting superrigidity here. But this is the basic idea. A subgroup is superrigid if all of its homomorphisms can be extended to homomorphisms of the groups it's contained in. That's what a superrigidity theorem is. And we'll talk about some interesting examples of that. But before I do, let me explain that what I've talked about in group theory terms actually is analogous to what we talked about in combinatorial terms. So let me just explain the analogy. It probably seems like I talked about two different things. And maybe people are welcome to ask questions or make complaints at any time, but are there questions? Yeah, go ahead and stop me if anything comes up. Okay, so let me talk about why these two topics that really seem quite different are just two different versions of the same idea. And so to do that, I need to restate, let me talk more precisely about what combinatorial superrigidity is. Remember, it said that if you make a copy of the object, obeying the combinatorial rules, then the copy that you made, so if you glue the sticks together properly, it has to have exactly the same shape as the original. Okay, that's what combinatorial superrigidity means, but let me rephrase that so that we see that it sounds more like the group theoretic version. So the key thing to notice is that when you make the copy of the object, you might not get exactly the same object. You've got a copy that looks like the original, so there's two things that might have happened. Maybe one person somebody made the original object here. When you copied it, it could be a different place. It could have been it could be rotated. And the thing I'm getting to, or it could be translated to a new spot. And actually what I left out here is or it could be reflected from what it was originally. So anyhow, the key thing to notice is that all those operations, rotations, translation, and then left out reflection, are all trivial modifications of the original object. And the reason I call them trivial is that rotations, translations, and reflections are all symmetries of the entire universe. Okay? So, of course, the rotations, translations, symmetries, they have nothing to do with our object. Those can be applied to any object. The entire universe, which in our case is the Euclidean space R3 is what we're talking about, they're symmetries of the whole space. And so let me say that yet another way. So what that means is, here's the key idea. Combinatorial superrigidity means that if you make a copy of the object obeying the combinatorial rules, well, here's my original object, I take it apart and put it back together, I might get something different, but the key thing is that same result, that new object, could be attained from the original object, not by taking it apart and putting it back together, but just by moving the whole universe to a new position. Just translate the whole universe across, or rotate the universe, or reflect the universe. The new object can be obtained just by applying a symmetry, in other words, by moving the entire universe to that spot, okay, to some new position. That's what superrigidity is. Anything you can do to an object by taking it apart and putting it back together can be done without taking it apart, just by moving the whole universe. That's what superrigidity is. So anything you do to the object, actually that object is glued so strongly into space that the whole universe comes with it whenever you try to move it. That's what superrigidity is. It's actually embedded just implicitly in space. All right? So that's what combinatorial superrigidity means. So another way of saying that same thing, if you can move the object somewhere by taking it apart and putting it back together, so if you take it apart, put it in a suitcase, and reassemble it in France, well, the entire universe could have just been moved over and that object would have been in France. Okay? The whole universe could move to that new position. Okay? If you can move the object somewhere, then in fact the whole universe can go there. That's geometric superrigidity or combinatorial superrigidity. And the point is, group theoretic superrigidity is really the same thing. Remember, to say that gamma is a superrigid subgroup means that if you have a homomorphism defined on gamma, then it can be extended to a homomorphism that's defined on the entire group G. And let me not worry about the stuff about existing closures at this point. That's a technical condition. Okay, that's what it means. And if you think of what this means in words, you can say the same thing by saying, suppose we make a copy of gamma. That's what this phi does. Phi will take gamma and make a copy of it as a bunch of matrices. So suppose you take your group gamma and make a copy of it that's a bunch of matrices. Well, that map phi will extend to be defined on all of G, so what that means is the entire group G can be moved into a group of matrices. So if you take gamma and make it as a bunch of matrices, in fact, that same copy can be obtained by taking not just gamma, but all of G as a group of matrices. And that's supposed to sound like what I said right up there. That if you make a copy of your combinatorial object, you can get the same result by moving the whole universe to a new place. So that's the analogy, that these two things really are the same idea. If you have a copy of something, you can get the same copy by moving the entire universe that came into a new place. So I hope that you can see that these two subjects are analogous. And also, I think it's clear that combinatorial superrigidity is something very important, or at least rigidity. I mean, when people build a scaffold, they want to know that it's not going to bend or break. So it's very important, for practical purposes, to know whether or not an object is rigid or super rigid. Yeah, if you're building toys, you want to know that when you construct, when people put them together, you always get the same thing. Combinatorial superrigidity seems intrinsically to be important. And one of the reasons for doing this analogy is that I hope that you'd believe that the same idea in some other subject would also be important. Right? So it's just natural to believe that the group theoretic superrigidity would be important to at least two group theorists. And in fact, there are geometric consequences as well, but I'm going to talk about a little bit of the group theoretic consequences. Okay, so the next thing I want to do is give some examples of superrigid subgroups. We already have one example. Okay. And the example we have is that ZK is superrigid in RK. And the trouble, though, is that this is just talking about abelian groups. And abelian groups don't get you very much in mathematics. I want to talk about some examples of non-abelian groups that are superrigid. But I think this is probably a good time for, let's just take a 5-minute break. Okay. So let's take a break. When we come back, I'll talk about some examples of superrigid subgroups.